Welcome, everyone. To Top Niche Market today, we're diving headfirst into one of the most exciting, controversial, and transformative milestones in modern science, the achievement of quantum supremacy. This wasn't just another incremental step in computing. This was our Wright Brothers moment. Think about it. When Orville and Wilbur Wright's flyer lifted off the ground at Kitty Hawk for just 12 seconds, it didn't carry any passengers. It didn't cross an ocean. It barely flew the length of a modern passenger jet. But in those 12 seconds, it proved that powered flight was possible. It turned science fiction into engineering fact. That single event sparked a revolution that within a single lifetime would connect our entire globe. The 2019 quantum supremacy breakthrough was exactly that, a short, wobbly flight for a new kind of computation, but one that proved we could leave the ground, forever changing our technological horizon. So, what exactly happened? In the simplest terms, a quantum computer, for the very first time, performed a specific calculation that even the most powerful classical supercomputers on Earth could not realistically complete. It wasn't about being a little faster. It was about operating in a completely different computational universe. This moment, broadcast to the world in a landmark paper, was the starting pistol for a new technological race. It was controversial, it was debated, but its impact was undeniable. It announced to the world that the age of quantum computing was no longer a distant theoretical dream. It had arrived. But this overnight success was, in reality, decades in the making. The journey didn't begin in a sterile Google lab, but in the mind of one of the 20th century's most brilliant and eccentric physicists, Richard Feynman. Back in 1982, Feynman looked at the natural world, the intricate dance of molecules, the behavior of atoms, and saw a profound problem. Our best classical computers, these marvels of logic and binary, were fundamentally clumsy when trying to simulate reality at its most basic level. It was like trying to paint a masterpiece using only a sledgehammer. They could approximate, but they couldn't truly capture the quantum essence of the universe. Feynman had a revolutionary idea. What if, to simulate a quantum system, you built a computer that operated on quantum principles? Fight fire with fire. Use the universe's own operating system to understand it. This was the seed. For years, it remained a beautiful but seemingly impossible vision. Then in the 1990s, the theory took a giant leap forward. A mathematician named Peter Shor developed an algorithm-Shor's algorithm that was a theoretical bombshell. He proved that a functional quantum computer could, in theory, crack the encryption that protects virtually everything in our digital lives, from bank accounts to government secrets. Suddenly, quantum computing wasn't just a tool for curious physicists. It was a technology with society-altering potential. But there was a catch, a colossal one. Building the hardware was a nightmare. The building blocks of quantum computers, known as qubits, are unbelievably fragile. A classical bit is a simple switch, either a 0 or a 1. A qubit, however, can be a 0, a 1, or a delicate superposition of both simultaneously, like a spinning coin before it lands. This fragility, this quantum weirdness, is its source of power, but it's also its Achilles heel. The slightest vibration, a stray magnetic field, or even a tiny change in temperature could cause the whole system to collapse from its quantum state into a useless classical one. It was like trying to build a sandcastle in the middle of a hurricane. For decades, the challenge seemed insurmountable. Moving from theory to a handful of fragile qubits was a slow, painstaking process of innovation. Then came October 2019. The world of computing held its breath. In a paper published in the prestigious journal Nature, a team from Google announced they had done it. Their quantum processor, named Sycamore, containing 53 meticulously engineered superconducting qubits, had achieved the impossible. Here's the task they set for it. They created a pseudo-random quantum circuit. Imagine a machine that flips 53 interconnected coins at once, where the outcome of each coin toss is influenced by all the others in a complex, probabilistic web. The task was to run this experiment and predict the most likely outcomes. A classical computer would have to calculate every single one of the 10 quadrillion possible outcomes, one by one. It's a brute force approach that would bring even the mightiest supercomputer to its knees. Google's Sycamore processor completed the task in 200 seconds, just over 3 minutes. Their team estimated that Summit, the world's most powerful classical supercomputer at the time, would need 10,000 years to perform the same calculation. Let that sink in. 200 seconds versus 10,000 years. A task started on that supercomputer when our ancestors were first developing agriculture would have just finished today. This vast chasm in performance was the basis for their claim of quantum supremacy. The problem itself had no immediate practical application. It was designed specifically to be hard for classical computers, but manageable for a quantum one. But that wasn't the point. Just like the Wright Flyer wasn't meant to be a passenger plane, this experiment wasn't meant to solve a real-world problem. It was the ultimate proof of concept. It was the sound of a new engine roaring to life for the very first time. But just as the champagne corks were popping at Google, a skeptical voice emerged from a titan of the old guard, IBM. IBM, a fierce competitor in the quantum space, published a blog post challenging Google's claim. They argued that Google's 10,000-year estimate was flawed. With a more clever, optimized classical algorithm, and by using a supercomputer's vast secondary storage, its hard drives, IBM contended that they could solve the same problem in just 2.5 days. Now, 2.5 days is still significantly longer than 200 seconds, but it's a world away from 10,000 years. This debate was crucial. It wasn't just corporate rivalry. It was a vital scientific discussion that helped clarify what supremacy really means. It revealed that this isn't a fixed finish line that, once crossed, is crossed forever. It's a dynamic, shifting boundary. As quantum hardware gets better, classical algorithms and hardware also improve, fighting to keep up. The classical world is not standing still. This controversy also highlighted the problem with the term supremacy itself. It sounds absolute, like a final victory. But the real goal, the more meaningful destination, is what the community now calls quantum advantage. This is the point where a quantum computer can solve a practical, useful problem more efficiently, more cheaply, or in a way that is simply impossible for any classical computer, no matter how long it runs. Supremacy was a demonstration flight. Advantage is when the plane starts carrying cargo and passengers. The world was watching, and the race was on. Google's milestone wasn't an endpoint. It was a global catalyst. Just a year later, in 2020, a team of researchers from the University of Science and Technology of China, led by Pan Janwei, threw their own hat in the ring with a completely different approach. Instead of using superconducting qubits like Google, the Chinese team used photonic quantum computing. They built a machine called Jiujing that performed its calculations using particles of light photons sent through a complex maze of optical circuits. They tackled a different, but similarly abstract computational problem known as boson sampling. Their results were staggering. They claimed their prototype was 100 trillion times faster at this specific task than existing supercomputers. Once again, this was a groundbreaking experiment, but it faced similar scrutiny. And just like with Google's claim, classical computer scientists got to work and developed better classical algorithms that narrowed that enormous gap. Each of these milestones, from Google's Sycamore to China's Jiujing, serves as a new high-water mark. They pushed the boundaries and forced both sides of the computational world, quantum and classical, to innovate. This isn't a single battle. It's a continuing campaign to map out the precise territory where quantum machines hold an undeniable practical edge. So, if these supremacy experiments are like abstract tech demos, when do we get to the real-world applications? This is the quest for quantum advantage, and we're already seeing the first tantalizing glimpses of it. The ultimate goal is to use quantum computers to solve problems that are existentially important to humanity but computationally crushing for classical machines. Think about drug discovery. Designing a new drug involves understanding how a complex molecule will interact with an equally complex protein in the body. There are so many quantum variables at play that classically simulating it perfectly is impossible. We rely on trial, error, and approximation. A quantum computer could, in theory, simulate this interaction at a fundamental level, molecule for molecule, electron for electron. This could slash the time and cost of developing new medicines from a decade to perhaps just months. We're not there yet, but the first steps have been taken. In 2020, Google's team used their Sycamore processor to perform the first ever quantum simulation of a chemical reaction, modeling a simple diazine molecule. It was a small molecule, but a giant leap for quantum chemistry. Then, in 2022, another milestone hinted at a different application: optimization. A team demonstrated a quantum approach to the vehicle routing problem, a classic logistical nightmare. For companies like Amazon, FedEx, or even your local pizza delivery, finding the most efficient route for a fleet of vehicles is a problem that grows exponentially harder with each new stop. For a handful of stops, your phone's GPS can handle it. For thousands of packages and hundreds of trucks, it becomes a problem that can choke a supercomputer. The 2022 experiment showed that quantum approaches have the potential to scale far more gracefully, promising a future of hyper-optimized supply chains, reduced fuel consumption, and more efficient logistics for the entire global economy. Now, let's get to the cutting edge. What happens when you merge the two most disruptive technologies of our time? AI and quantum computing? You get quantum machine learning, or QML, a field that began to truly emerge as a frontier in 2023. Classical machine learning is incredibly powerful. It finds patterns in data. But what if there are patterns that exist in a way our classical computers can't even perceive? QML operates on the principle that quantum computers can process information in a vast, high-dimensional space called a Hilbert space. To put it simply, a classical AI might be able to analyze a photograph pixel by pixel. A quantum AI could analyze the fundamental quantum information from which that photograph is just a single collapse outcome. It's like being able to see not just a shadow on the cave wall, but the 3D object casting the shadow in the first place. This could allow us to detect subtle correlations and patterns in data that are completely invisible to even our most advanced classical neural networks. The potential applications are breathtaking. In finance, it could lead to models that predict market fluctuations with unheard of accuracy. In medical imaging, a quantum neural network could potentially analyze an MRI scan and detect the quantum level signatures of a disease, like cancer long before a physical tumor is visible to the human eye or classical algorithms. As these experimental systems mature into practical tools, they won't just improve our current industries. They could fundamentally revolutionize them by unlocking entirely new ways to analyze data and optimize the world around us. But before we start planning our quantum-powered future, we have to be honest about the colossal mountains we still need to climb. This road is paved with immense challenges. The single greatest enemy, the one that keeps quantum physicists up at night, is error correction. As we discussed, qubits are fragile. They exist in a state of delicate quantum superposition that can be destroyed by the slightest environmental noise. This decoherence introduces errors into the calculation, rendering the results useless. The machines we have today are part of the Niski-era noisy intermediate scale quantum. They are powerful, but they are also loud with errors. The solution is fault-tolerant quantum computing, which requires a massive overhead of physical qubits to create a single stable logical qubit. It's like having a team of 10 people constantly checking each other's work to ensure one person's mistake doesn't derail the whole project. Early advances in 2024 have brought us closer to this goal, but the scaling required is immense. To solve truly complex problems, we won't need hundreds of qubits. We'll need millions of stable, interconnected, fault-tolerant qubits. That remains a profound engineering challenge. Despite these hurdles, the economic motivation is enormous. Projections estimate that quantum computing could unlock between $450 to $850 billion in annual value by 2035, impacting industries from pharmaceuticals and materials science to finance and logistics. That kind of potential is a powerful engine for innovation, driving billions of dollars in research and development to overcome these very challenges. Every great technological leap comes with a shadow. For quantum computing, that shadow is long and dark, and it falls directly on the very foundation of our modern digital world: encryption. Remember Peter Shor's algorithm from the 1990s? It's not just a theoretical curiosity anymore. A large-scale, fault-tolerant quantum computer running Shor's algorithm would be a universal master key, capable of breaking the RSA and elliptic curve cryptography that protects our bank accounts, our secure communications, our government secrets, everything. The digital locks that secure our civilization would simply crumble. This has triggered a desperate race against time. While one community is racing to build a quantum computer, another is racing to build defenses against it. This field is called post-quantum cryptography, PQC. The goal is to develop new encryption standards that are secure against attacks from both classical and quantum computers. In 2022, the U.S. National Institute of Standards and Technology, NIST, announced the first set of PPQC standards, marking a critical step in the global effort to upgrade our digital infrastructure. The race is on to deploy these new defenses before a cryptographically relevant quantum computer arrives. Beyond security, there's a human challenge, a global shortage of quantum talent. We are building a new industry that requires a new kind of expert physicists, engineers, and computer scientists who can think in the strange language of quantum mechanics. Educational programs and global initiatives are ramping up to train the next generation of pioneers who will build and program these incredible machines. So where do we go from here? The path forward is from today's noisy, experimental NISC devices to the robust, fault-tolerant systems of the future. This means scaling from hundreds of qubits to hundreds of thousands and eventually millions. It's not yet clear which technology will win out. The race is on between several competing platforms: the superconducting qubits used by Google and IBM, the trapped ion systems that offer higher fidelity but slower speeds, and the photonic approaches pursued in China. It's possible that the future isn't a single winner, but a hybrid world where different types of quantum computers are used for different tasks, often working in tandem with classical supercomputers. Experts are cautiously optimistic, with most predicting that we will see true, practical quantum advantage for specific high-value problems within the next 5 to 20 years. It won't be a single light switch moment where the world changes overnight. Instead, it will be a gradual but accelerating revolution as quantum solutions begin to outperform classical ones in one industry after another, reshaping our world in ways we are only just beginning to imagine. The story of quantum supremacy is more than just a tale of technology. It's a profound lesson in human ingenuity. It teaches us about the power of a long-term vision, starting with Richard Feynman's seemingly impossible dream. It reminds us that progress is often messy, controversial, and non-linear, as shown by the healthy debate between Google and IBM. And for our own lives, there's a powerful takeaway here. We are all living through a period of exponential change. It is easy to feel intimidated by concepts like quantum computing, to dismiss them as things for geniuses in labs. But the lesson here is to cultivate curiosity, to ask questions, to not be afraid of the complex, and to try to understand the why behind the technologies that are shaping our future. Just as our ancestors looked to the skies and dreamed of flight, we must look to the strange and wonderful quantum realm and prepare for the possibilities it will unlock. We don't all need to be quantum physicists, but we should all be curious citizens of this new horizon. I want to leave you with a couple of questions to think about. If you had access to a powerful quantum computer, what real-world problem would you want to solve first? And as a society, how do we ensure that this incredible power is developed responsibly and used for the benefit of all humanity, not just a select few? Thank you for joining us on this journey into the quantum realm. I hope this has sparked your curiosity and given you a clear vision of the incredible future we are building together. And if you enjoyed this deep dive, please consider liking this video and subscribing to Top Niche Market for more episodes exploring the frontiers of science and technology. We'll see you next time.